say 3, 4, 6. The goal is to predict properties of materials and molecules because electrons are waves, right? You already are certified experts in Schrödinger way to predict future by expansion coefficients. There are also like useless but correct Feynman ways through evolution operator, and now we enriched our skills by Heisenberg way to predict future, where one does not predict the overall future but focus on only one property and sets up the equation, the Heisenberg equation of motion for observable that one wants to do. Why are we doing it, and what is the practical goal? We do need to solve a little scientific problem that we were discussing here in class. What would happen if we inject single electron in the universe where it's only vacuum, now one electron? If you inject it localized, will it shrink or expand? Will it move with acceleration, deceleration, or constantly? And Schrödinger equation of motion, Heisenberg equation of motion, will help us to prove that if you move with constant speed. The plan is to get support for this result today, and if time allows, even start new chapter. So here are presentations. Friendly reminder, I look forward to see your slides on Thursday midnight. And on Friday, we will present them 5 minutes per presentation. The goal is that if anyone was missing specific lab by listening to this set of presentations, we all will know what to do with this method and replace mathematical derivations with very simple running of and adjusting of scripts. So here is the equation itself. So if one looks for the operator and one knows the operator of total energy, then one can set up how the operator changes in time. And for our practical purposes, we always put angular brackets here, but it works without them as well. So here is the last slide if we are short in time, and maybe last slide that belongs to this subject of Heisenberg equation of motion, predicting shape of the direction of motion of the injected electron. So the idea is that I should announce that if everything is clear here, one can stand up and do it. And so maybe after going over all elements on this slide, the rest of the meeting is not needed. At least I can try, and then if you go into the details. So at the top, there is the universal equation. And since we are interested in the center of the this distribution for an electron, we need to plug in x into this A, where we have A here and there. And in order to practice this equation, we will need to find commutation between total energy for electron in this space and operator of position. So if you carefully do it, one will find out that this commutation will reproduce momentum operator wherever we see this derivative over space. By playing with constants, we can bring it to the momentum P. And then the equation of motion for expectation value of position will be increment of position in space will be equal to momentum over mass, which is velocity, right? like momentum is velocity times mass, momentum divided by mass is velocity. There are two things to note and mention. So instead of regular high school position and momentum, those are expectation values. So when writing these equations, we are playing kindergarten childish games, like solving so simple equations, but we are understanding that it is equation of motion only for the center of distribution, where it is a quantum particle that may perform some exotic things. So by good luck, it looks very simple, but with simple equation, we describe complicated stuff. And then if we want to solve this equation, we need to know what will be the momentum expectation value as function of time. And here it gives the reason that we cannot do only one branch. We need immediately start seeking for equation of motion for momentum, which then after solving we are going to plug into here. And in order to, if on the right branch, we are setting that A equals P. So we plug P into here. P into here and into there. And then if one notices that total energy is just square of momentum because there's only kinetic energy. And there is a theorem, if one makes commutation of the same operator in the different power, it will go with zero. So one is finding that commutation of total energy and momentum is zero, therefore time derivative of momentum is zero, right? And then one integrates this equation and finds that momentum as function of time is constant, right? Integration of zero is constant. And then this stuff is plugged into here. So if momentum is constant, we do not need to do any special things. We just treat it as constant and integrate left and right part and get linear growth with time, starting at initial position, and then pace of increment is just value of momentum. So basically it is the 15 minutes compressed in 2. And since I was preparing slides, I need to go over them. If you understand all these ideas, I will be just entertaining myself. Let's check if there are any questions online. So Adam, Fuller, Spencer, Kennedy, do you have any questions about the material that we went over this summer slide? Or you're okay if you go forward? It's hard to listen in the mask. Please type or say if you have questions or you want to speed up or slow down the narration. No signals, no question. Okay, thank you, Spencer. Okay, then we'll go forward. And by the way, now I speak not as an for just a little break. I am speaking not as an instructor of the class, but as a selfish leader of the research lab. If anyone wants to participate in research and get paid, just contact me in person. I always forget it during the class, and then it is too late after semester is over. So let's go forward. So I did mumble all details. So it is if you were taking notes and carefully following this summer slide, you will not find anything surprising. So for the right branch, we need to find how the momentum commutes with energy. So instead of energy is we were proving momentum operator squared with this constants over mass, and it is. And then if you don't forget, don't remember where this kinetic energy comes from, it's just p square over. It's regular as one defines. And then if one writes down here, like momentum in the second power, momentum in the first, minus momentum in the first, momentum in the square. So we do not violate any commutation rule. If you type write PPPP minus PPPP, it should be 0. I think it is quite convincing over there. And if one wants to write this stuff rigorously, then one plugs it into Heisenberg Equation of motion, find the commutation is 0, and then we integrate left part, and we integrate right part. And then momentum as function of time is whatever it was at the beginning, right? So we have done this right side, and we can use it in going forward. So here one plugs in operator equals position, and one needs to find commutation between total energy and position operator. So if I do have doubts and discomfort in these commutators, which quite natural for humans, this theory is a little weird and counterintuitive and not natural in a common sense. So if I feel any conflict thinking about it, the right way to do commutations is to artificially plug in function of x to the right of this to the right side of the left and right part, and then just practice differential operators. So the stuff, the constants up front, kinetic energy, second derivative of space, position, and then we ha minus AH. So second derivative x and then phi, then x, second derivative phi. So if you want to find the commutator, we need to carefully practice these derivatives by regular rules of derivative of product, right? So here we just apply derivative from left to the right. So in the first term, it applies both to this x and to the function of x, and here it applies only to the function of x, right? I think it's quite boring going over slides, right? So we need this Hamiltonian comma x d2 dx squared x, and then phi h minus h bar squared to m d2 dx squared x phi minus x d to dx squared over 5. So for the first term, I will first derivative out of bracket, and then inside the bracket I take first derivative. So d dx of x times 5 plus x d dx of 5. So all the stuff was here, then minus x d to 5 dx squared. We are not going to, there is nothing to change in the last term. And now for the first term, one needs to practice derivative of the product 2 times. So applying derivative to here, one is getting, and by the way, dx over x, this little thing will be 1, right? So we are having dx. If it is 1, we do not need to really practice it for the first term. Then for the second term, we do have ddx of x times ddx 5. And then the one more term will be x d2 over d dx squared 5 minus x d2 5 d dx squared. So I do see that last 2 things are canceling. Here, check this dx over dx will be 1, and then we can cancel stuff here and put just factor 2. So after canceling last 2 terms, the only answer will be 2 ddx of 5 of the function, and one needs to keep the stuff in front. So it will be minus h bar squared to m times 2 d dx. And originally I was putting phi in here, but now I can remove it because I just play with operators. Cancel 2. Make sense? I hope and wish we will not have homework on such derivations, but I'll check what is on my phone. Okay, let's go forward, and maybe there will be the same thing, just in a better calligraphy. So 2 terms from commutation. For the last one, nothing changes along the whole lines. And for the first one, we practice derivative of product once. And then we practice, the first term is not changing anymore. And then we practice derivative of the product twice. And then there are 4 terms. First derivative of function, first derivative of function, and then x second derivative function minus x second derivative function, which cancel. So no cheesy fake line, right? Everything is clear. And if we carefully process, if we remember that by our derivation, by derivation of Heisenberg, one should have the imaginary unit of h bar, I over h bar. If one combines it with the factor h bar square over m, so h bar cancels, and as a result, one is, and also one may plug in the definition of momentum. So wherever we have I h bar ddx, we can replace it. So by manipulating, so we have once from this h bar square, one is removed because of factor in the equation of motion, Heisenberg equation of motion, and another one is eaten away because of definition of momentum. And then we do have, we plug it everything in, and we have time derivative of expectation value of position is just expectation value of momentum divided by mass. Let's check if there are any questions at this point. No questions one, no questions two, no questions three. Go forward. Okay, I think I just enjoyed this stuff and wrote it down several times in the holographic way. So by plugging in position into instead of A, one is getting this equation of motion. And from our previous consideration, we do know that momentum for the free space is not changing. So we can plug in that P equals P, expectation value of P at time equals 0. And then this integration becomes trivial, just integration of a constant. Here, this little cross is not like remove, cross it out, but replace A with X. And then after we do have equation of motion, we can practice integration of the left and right parts. The standard thing that we all were offered to do in like high school physics and college physics, and which is just naturally follows from differential equations. Okay? Integrate left and right, and then we get the answer that position center of the distribution for this wavy electron, if it moves in a free space, goes forward with constant velocity. It doesn't accelerate, doesn't decelerate, doesn't turn back. So it just goes forward with constant pace. So it's the last line is the summary. Momentum doesn't change. Position expectation value goes forward. And when we had a skinny distribution, it becomes fat. Skinny becomes fat for width, and it moves forward with constant velocity. So by now we are done with chapter 2. And we can actually start next chapter. So relax and lean back. There will be nothing serious. I hope that there are all reasons to believe that there will be successful presentations on Friday. You'll be able to leave behind a substantial part of math and do just running of the codes. And from overall navigation through the class, there is very natural question that you may have asked yourself or developed irritation against the instructor and wondered why it is not answered. So if you leave behind natural human wish to do nothing and relax, and you just live inside the course, and you analyze what is going on and what is promised and what is done, do you see any discrepancy? Try to be critical. Not, of course, we should be all friendly and forgiving to each other for all mistakes, but if you want to be super critical, do you see any discrepancy what was posed as goals and promised and what is being done? Try to be very critical. I'll repeat what was promised. The promise was to help identifying and predicting properties of real molecules, right? I'm not rejecting, I'm admitting I told it. On one hand. On another hand, we are wasting energy of young brains onto some auxiliary non-existing space, universe where there is only one electron. It looks like a little discrepancy. The promise was to discuss molecules, and in reality, we do math and abstract spaces.
Well, if we don't do that math and abstract spaces, how are we going to understand molecule? Start small and grow up, right? You said
Exactly. Yeah, I'm very grateful that you are so forgiving to the instructor in the course. Yes, it is a logical path, but if consider the audience of students as persecutors on the court, telling the instructor is guilty, doing not what is promised. So from this point of view, one day one needs to return back from this auxiliary space where there were no borders into something realistic. And realistic means that electron is not free. So it either hits the wall or it is attracted to ions in molecule. Or maybe there is a different groups of ions, like which attract stronger in one area and weaker in the other area. And then electron will prefer to stay in the areas of space where it is attracted better. And then we'll come to concept of electron transfer, electronegative, polarization, stuff like that. But we definitely need to bring something that either repel or attracts electron. So before our total energy operator did include only kinetic energy. And as time goes by, we need to introduce potential energy. So it is the biggest miss in what we did for 15 lectures. We didn't have potential energy. Now it is time to introduce it. Yes, we will do baby steps, slowly but surely. But general direction is in this way. So if you browse in the space of ideas, then we do have this evolution operator, Heisenberg Equation, Heisenberg Equation of motion. We have models and one electron in free space, and we practice Heisenberg Equation and Heisenberg Equation of motion. So we have two wins in our career. One can apply different methods to free space, but it would be not very related to applied life. We can try to build up set of models, more and more complicated, more similar to realistic molecules, and try either one of these tools. And maybe if one of these tools, neither one of these tools will be applicable, then we may need few more concepts and tools as we go. If no, it's okay. But I'm acquainted with the rest of the notes for the rest of the class. There will be a couple of modules. And at the very end, we, for the most of the course, we will consider so-called isolated systems, where there is electron, there are some like nuclei or walls that attract or repel it, and everything develops like in a glass container isolated from outer world, which is also not a truth. In true life, experimenters inject new compounds, kick substances with hammers, heated with burners, irradiate with radio frequency in NMR or optical frequency by lasers. So there are external perturbations that need also to bring in if you want to be really practical physical chemists related to whatever happens in real life and in wet chemistry. So the next, I would say, like couple, 2-3 weeks, there will be a concept of still one electron in the box. So I'm going to start whatever minutes are left. I'm going to start speaking about the concept of the box. And if you were browsing or just flipping pages of any text, you may have noticed that any textbook in physical chemistry quantum theory does have this concept of particle in the box. If, for example, if you make a team and decide to include quantum theory into high school program, which is sometimes included, just very little notes, but for most it is excluded. If you want to really digest and summarize and put a minimalistic amount of information that would be digestible by high school students. So we will leave everything except time independent Schrödinger equation and electron in one-dimensional box. So it is, I wouldn't say that it is most important for real life, but it is the simplest implementation of physical chemistry and quantum theory. So we are going to do really, well, it is not like simple, but it is the simplest possible section of quantum theory. And I'm going to chat a little how it is related to real world. So there are some ugly scratches of myself from previous years. And here is the idea. If the electron is free, there is no potential. But if there is an ion with positive charge, it will attract the electron, which means before our potential energy was 0, and if there is something really attractive, like a coach, it creates a dip in the space, or the electron stops and doesn't want to leave. So each ion, each positively charged positive ion is a little dip in the potential. If you have a group of ions, if you have like skeleton of a molecule, it is just several dips, several potentials. And then electron decides at which ion I want to sit, or I want to sit on 2 chairs simultaneously. Like electron is shared between ions. And let's check and consider one more hypothetical situation. Suppose we have a molecule in a vacuum. And then in the region of space where we do have a molecule, we have so many dips in potential. In the region of space where we do not have, where is empty space, it is the same as it was before, just potential is 0. So it's 0, 0, 0, and then dips. Right? So in average, electron would be happier to sit on the molecule rather than floating around in the vacuum. It will be, if we inject it into this universe, it will find where the molecule is and sit there. But going through details of each individual ion and each molecule is a very noble task, and we will put it in our to-do list, but not as a starting point. As a starting point, we will consider just regions of space where potential is 0 and regions of space where it is a little lower, which means there are so many ions, and in average, electron wants to be in this space. So if we look on the one-dimensional distribution, on the x, it will be like x-axis. Then it is just 1 squared d. If you do the same thing for x, y, and z, then it will be like or a rectangular U-Haul box for moving. Inside the box, it will be more comfortable, outside less comfortable. So therefore, it is named particle in the box. Right? So if the energy of the electron is not sufficient to climb up, if it is already inside the box, then one can make an approximation that height of this walls is infinitely high, just for mathematical simplification. And then it is encaged literally inside the box, and it has zero probability to be outside. And this is one of the problems that can be solved exactly. And totally, there is like a handful number of problems that can be solved exactly without a computer. It will be one of them, and it is a perfect study material. What? In one, if it is one ion hydrogen, those are just details. Like there is a electron is not literally falling; it will be just rotating, and we will cover it at the end of the course. And the shape of the potential is like coulombic 1/r, which is too hard for the beginning. And here are a couple of examples. So that I want to bring up a statement that particle in the box that we will focus our effort mathematically and with help of the computation is not a spherical course in a vacuum. So it is not abstract 2 completely deprived from reality. There is a broad class of realistic materials which can be explained, their properties can be explained with relatively high precision, just staying within the concept of the particle in the box. So let's chat about politics and history. What's the political system in the United States? How would you define it with one word?
Democratic Republic.
Okay. What is the political system in Britain?
Monarchy.
Okay. Monos means single in Greek. Archy means main principle, so single principle, right? What was the political system in ancient Rome? I want to bring up a word that is not formal, but it is often used when people want to give a negative connotation. Like if the state is corrupt, there are rich people who grabbed power, and it is less democratic. They are like a little circle. So
Oligarchy?
yes, oligarchy. Super, super. So
Bad chemistry.
yeah, it is what we should discuss in chemistry. So I don't know if any of you guys have minors in polymers and coatings. You do? Okay. It is a very successful department that have they do not have teaching. The teaching program is reduced, but research is extended. They get a lot of grants, and it is a natural career path. Just get masters right after undergraduates there. They generously pay. So if we just think about polymers, there are regular polymers just for plastic bottles, and there are conductive polymers which are used for OLEDs, like OLED TV. So if we have polymers are composed of several repeating units. But if one chemically depolymerize, so then it will be a single unit of polymer. What would be the name?
Monomer.
Yes, monomer. Even if there are two units are connected together.
Dimer.
Yeah.
Trimer.
And then one needs to practice one of the ancient languages. either Greek or Latin, like tetramer, pentamer, hexamer. But if it is really a lot, close to infinity, one tells polymer, many, and if there is a few, what's the name?
Polygonal.
Exactly. So if one combines not infinite chain, but few, it will be exactly an example for using particle of the box. So along the polymer or ligament, along the ligament, electron feels comfortable as long as there is a chop, it is chopped, electron doesn't want to go away from the wall. There is a like vacuum or solid. So electron is enclosed from head to tail, from tail to tail, bumper to bumper. So electron is staying inside this oligomer. And we will learn through this chapter that by modifying the length of the oligomer, modifying the size of the box, chemical properties of this object drastically change. So one can, chemical and physical properties, so one can perform them differently just by tailoring the length of the chain. Well, anything that has borders. So when you know there are like gold, metal particles which fluoresce or bioimaging. So inside electron is happy, outside is not. Or there are semiconductor structures for quantum dot TV. It's the same. It's not one dimensional; it's three-dimensional box. But again, for this object's particle in the box concept is really fruitful. Here's an example of one maybe more realistic. Like polyene is too simple. Here is PPV. I'm not chemist by the training. Any polyene, the new oligomer. PPV.
Okay, yeah.
With one benzyl ring and like two carbons in between.
Polyphenol model.
Yeah, super. Whew. Oh, okay. Oligarchy, oligomers, right? Yeah, and another example, which I think I'm already all over time, is when we all our electronics, like cell phones, computers, are built on semiconductor silicon chips, or semiconducting elements of transistors are connected by metal bridges and isolated by silicon dioxide like insulating layers. So if one has two insulating layers and one semiconductor layer in between, it is also in Z direction. It is an ideal implementation of particle in the box. Or one physically makes bottoms and make electrons go up and down. Okay, even if I'm not done with this little story, we're done. Looking forward to see you 5 p.m. QBB 132. Complete. And everyone is welcome to depart to disconnect. Okay, bye-bye. See you.
Thank you.
Thank you.